I'm really excited to present our survey on deep learning applications for COVID-19. Compiling this literature review was about a 4-month effort of looking at all the different ways where deep learning systems have been implemented to aid in some specific area of COVID-19 relief. These includes applications like misinformation detection, scientific literature mining, precision diagnosis and medical image analysis, and epidemiology models like spread forecasting to give a quick sense of what applications will be covered in this survey. Throughout the survey, we'll contextualize these applications by reviewing the current state of deep learning. What are some of the core drivers that are helping deep learning advance so quickly? What are the key learning task variants like self-supervised learning compared to reinforcement learning? And then what are the key limitations of deep learning, namely interpretability, generalization metrics, learning from limited labeled datasets, and data privacy. So I really hope you enjoyed this presentation of our survey, Deep Learning Applications for COVID-19. Hopefully after watching this, you'll have a sense of some research projects for how you can help with some specific area of COVID-19 response. Our survey begins with a background on some of the other survey papers that have been released that cover either data science to combat COVID-19 or machine learning to combat COVID-19. Uniquely to these surveys is our focus on deep learning. We're the first survey to really specifically look at deep learning technologies compared to, say, data science as a whole. Then we'll discuss learning variants. By this we mean different ways that learning tasks are constructed, the most popular of which is supervised learning, where we fit these labels to our data, or we have unsupervised learning where we look for clusters. Then we have self-supervised learning, multimodal learning, where we combine different data modalities like images and text, reinforcement learning, and just to get a quick sense, we'll dive more into this later in the presentation. Then we'll go through 4 key areas of applications of deep learning: natural language processing, computer vision, life sciences, and epidemiology. Then we'll contextualize this with the limitations of deep learning, where we discuss interpretability, generalization metrics, the challenge of learning from limited labeled datasets, and data privacy. Then we'll end with a discussion on some of the things that I've learned and taken away from this comprehensive literature review of all the different ways deep learning has impacted COVID-19. Before diving in deeper, here's a quick sense of the applications that will be covered. Within natural language processing, we look at scientific literature mining, where we have data sets of scientific papers and we want to develop information retrieval systems, fact verification, question answering, or maybe even abstractive and extractive summarization systems. We'll also look at the automated construction of knowledge graphs, misinformation detection, and public sentiment analysis. Within the scope of computer vision, we'll begin with medical image analysis, particularly looking at how chest x-rays have been used to diagnose and help with prognosis of COVID-19 symptoms, particularly with respect to lung pneumonia. Then we'll look at ambient intelligence. This phrase is derived from a really great survey paper that came from Stanford University and authors such as Dr. Fei-Fei Li, who helped pioneer the ImageNet dataset. Ambient intelligence is describing this idea of having cameras all around hospitals that help with efficiencies, recording data, and overall getting a better sense of how the hospitals are running. It includes applications like detecting hand washing, helping to monitor patients in the ICUs to prevent ICU-acquired weaknesses, and all these little applications that we can imagine of having computer vision integrated within these hospitals and care spaces. Then we'll look at vision-based robotics. Robotics already is pretty good at manufacturing and things like that, but enabling it with vision is a really exciting idea. We've seen some really amazing advances where it can just take in pixel inputs. And particularly, how does that change the robotic space? Well, it lets you adapt to more kinds of tasks, more kind of variants with respect to the inputs. Say it's sorting objects. If you have a previously robotic system that's used to this one type of object, it can't generalize as well as these deep learning systems. So we'll discuss particularly how vision-based robotics is different from previous approaches to robotics and how it can help with different COVID-19 relief areas like the economic burden and disinfection and all these kinds of things. We use the term life sciences to cluster together some pretty different applications, but kind of have a similar theme where, say, we have healthcare data like precision diagnostics and trying to use genetic information or all kinds of information to have this deep learning system mine a better diagnosis and prognosis of symptoms, compared to, say, protein structure prediction, molecular property prediction, these biochemistry applications that differ enormously in how the data is set up compared to healthcare data. So we start off with precision diagnostics. This is the healthcare data. Particularly, we look at how we can maybe improve upon RT-PCR testing with deep learning systems and using more patient information. Then we'll look at protein structure prediction. AlphaFold 2 made news headlines of this amazing breakthrough and how you can predict the structure of a protein from the amino acid sequence. So why is this so interesting for COVID-19? DeepMind, they document how they use their previous AlphaFold 1 system to quickly predict the structure of these spike shell proteins on the COVID-19 virus. And this is useful compared to, say, experimental verification because it's much faster. If you do things like the cryo-electron microscopy to get the structure, it takes much longer than having the amino acid sequence of the virus and then quickly producing the structure prediction. And then that helps with predicting binding targets for our next application area, which is drug repurposing. So developing a brand new drug to combat COVID-19 from scratch, it would be really expensive. There's something like $3 billion is the cost of taking a brand new drug to market with respect to clinical trials and all this stuff. So what they'd rather do is repurpose an already approved drug. So look at how they use knowledge graphs, particularly to query the literature and try to see how they can, say, inhibit binding of one thing without causing these other side effects and all this kind of mining that's required to repurpose a drug for COVID-19. With respect to how deep learning can impact spread forecasting and epidemiology, we basically look at 3 different levels of how detailed the data is. In black box spread forecasting, we basically just treat it as a sequence of numbers, and we're just modeling the sequence of numbers, but we can also add further structure by, say, having this sequence of numbers but in nearby counties and countries, and having more detail with respect to how many different regions we're collecting this sequence of infected numbers. With the SIR modeling, this stands for the susceptible, infected, and recovered populations. It's a way of breaking up the population, adding more structure to the model by modeling the different subgroups of populations that are progressing along with getting infected with COVID-19. And then contact tracing would refer to having an extremely detailed data set where we could have so much data about who's coming in contact with who, and then maybe have this graph structured data. We'll look at a paper that particularly looks at having this graph structure that would be enabled by having contact tracing data sets, and then how you could use that to have personalized risk infection. So that's a quick preview of our application surveyed in natural language processing, computer vision, life sciences, and epidemiology. At the end of presenting these applications, we'll review some limitations of deep learning. These include interpretability, how can we understand why the deep learning system has made the prediction it has, generalization metrics, how can we trust it once we deploy it into the wild, and what kind of examples might it fail on. Then learning from limited labeled data is a huge theme in a pandemic response situation, especially with, say, medical image analysis where we don't have much data at the beginning of the pandemic. Then we'll look at data privacy. Obviously, we'll look at ambient intelligence. The idea of having cameras all over the hospital, it might improve operations, but it might also make people feel a little uncomfortable if they know that everything they've been doing in the hospital is collected in some centralized database. So we'll talk about particularly federated learning, ideas to get around that idea of having some centralized database, and other ways of ensuring more privacy with collecting the data required for deep learning systems. So as a quick reminder, this is the organization of the survey. I have about 78 slides for this presentation, so I expect this to be a very long video. So it will be time-stamped in the video if you want to skip ahead to particular areas that are interesting to you. As a background, these are the applications that we cover compared to other survey papers reviewing the use of data science and machine learning for COVID-19. So our applications are not all encompassing. There's more to it, things like how machine learning could be used for, say, like acoustic diagnosis. They do things like monitoring the breathing and then seeing if that's useful for diagnosis. But we didn't really think there was too much on that to include it in our survey. But there's a lot of other things, maybe even like vaccine development and how deep learning can help with that. There's a lot of other areas. So, even just this one, tracking the evolution of the virus and seeing the mutations. There's a lot of different applications of COVID-19. So I also highly recommend checking out these other surveys. And then one other thing to note is how they organize the applications. So particularly we've organized it by natural language processing, computer vision, because this is kind of natural to deep learning researchers. It's, to have different applications in computer vision, you can derive a lot of the same techniques. Like we have the same kind of self-supervised learning, say ImageNet pre-training, or with natural language processing, how we have this language modeling step. There's a lot of similarities with respect to sharing the same kind of data domain, whether that's images or text. So for that reason, we organize a survey in natural language processing, computer vision, and so on, whereas other surveys organize it based on, say, clinical applications, society-level applications, or molecular applications with respect to the COVID-19 disease and the SARS-CoV-2 virus. A major area to make advances in deep learning is exploring the different ways to set up a learning task. So the learning in deep learning refers to how we're going to learn this representation of the data through some kind of task, whether we have some kind of loss function, we have some kind of gradient update that updates this representation to align it with the task it's being asked to do. So here are kind of the 3 most common ways of constructing a learning task for deep learning. Supervised learning is the obvious, most well-known way of doing this, is where you have manually annotated labels. So a human goes through the data set and labels each, say, medical image or each question-answer pair. So you manually label this, and then you fit this loss function with this predicted y hat minus the ground truth y, and you use this to learn this representation. So unsupervised learning isn't about using labels. You can look for intrinsic structure in the data, like clustering algorithms, and maybe this is more useful for after you've already learned a representation through one of these other learning tasks. So it's common to say, use supervised learning to train a classifier, and then you use algorithms like TSNE or UMAP to try to visualize the structure in that representation. So in deep learning, unsupervised learning is more of an after step once you've already learned the representation through one of these other learning strategies, with supervised learning being by far the most popular way of doing this. But self-supervised learning is gaining a lot of momentum, particularly because often the case with deep learning is you have a small labeled data set with respect to these manual labels, but you have a massive unlabeled data set. So the idea is that you have some kind of algorithm to construct a ground truth label so that y hat minus y, the y isn't derived from manual annotation, rather it's algorithmically constructed, like say predicting positive pairs in contrastive learning, or rotating an image and then predicting the rotation angle. So transfer learning isn't really a new kind of learning task. It's really similar to the idea of how self-supervised learning is really played out. Transfer learning describes first training a model on one task and then transferring it to the next task. So it's common to start off with this algorithmically constructed with respect to the labels in self-supervised learning, and then transfer those weights to supervised learning. So in computer vision, this is often done by having ImageNet supervision, and then you transfer it to some new task, and then increasingly is being used for data sets like, say, there's the ChexPERT dataset, ChexPERT, and the X is capitalized in the middle of the name of the data set, where you would use that data set to do self-supervised learning, and then you would transfer those weights to your small COVID-19 labeled data set. So transfer learning just describes this phenomenon of training first on one task and then transferring to another task. Multitask learning is different from this because you're training simultaneously. So in multitask learning, say you interleave self-supervised learning updates with supervised learning updates. So say epochs, 1 through 3, the model is fitting the class labels, and then 4 and 5, it's doing contrastive self-supervised learning. Or in the same step, it has to optimize two loss functions simultaneously. So it's common to have these deep learning systems that have, say, like 3 or 4 loss functions to optimize as it processes each image or text sequence or something like that. So then weakly supervised learning is using heuristic labels for data. So it's not quite the same as self-supervised learning, where the ground truth label is so heavily constructed from the task. Weakly supervised learning describes things like programmatic labeling, where say you train on a little bit of labeled data and then you use that to infer the labels for the unlabeled data set. Or maybe you have some kind of heuristic, like in, we'll talk about knowledge graph construction, and they have these heuristics to try to construct label pairs of relations by kind of inferring that just if there's a verb and 2 nouns, treat that like it's a relation and then fit models and see what happens with that. Multimodal learning is another important theme for our surveyed applications. This is where you're combining representations learned in, say, images with text, or say you have medical images as well as the electronic health record information, and you're trying to do something like medical image diagnosis or diagnostics with, say, the RT-PCR testing system. You want to try to combine 2 different data domains. And this is pretty cutting edge trying to do this. Recent advances from OpenAI like Clip and Dolly, those are 2 of the most breakthrough advances in combining images and text. And there is a comprehensive body of literature that is trying to do vision language modeling, but it's not the easiest thing to do, to say. And then reinforcement learning is this really exciting area where you're optimizing a reward with respect to a series of action decisions. So it's challenging because you have several decisions to make or several predictions, and then you receive a sparse feedback. So you make several decisions, and then you get your reinforcement, your reward of how good your decisions were. And this is challenging because you don't get feedback on each immediate state to action decision that the model makes. So we'll talk about all sorts of different things, particularly diagnostics and robotic control can benefit enormously from reinforcement learning. Before we begin diving into the applications of deep learning for COVID-19, these are a few of the massive drivers of progress that I'm seeing in deep learning. So the first is self-supervised learning, where we're seeing first pre-training on some massive unlabeled data set with an auxiliary task like particularly contrastive learning, where we're trying to make representations of positive pairs similar and negative pairs dissimilar. And this is mostly powered by data augmentations. But this is making huge advances in how representations are being learned with deep learning. So another really great paper is titled "Don't Stop Pre-Training." And particularly the lesson from that paper is that the in-domain composition of this massive unlabeled data set that powers self-supervised learning is very important. So to give an example, in medical image analysis, ImageNet pre-training isn't that useful. You want to have some kind of medical image data set that is massive and unlabeled to do the pre-training. You don't want it to be a completely unrelated domain. And that's true for these language modeling. Say you're language modeling Wikipedia text compared to scientific papers. It's not going to be as useful for a scientific paper downstream supervised learning task when you're doing that transferring. So then another massive driver of progress is the transformer neural network and the attention layer. So even after this survey was published, transformers have started making their way into computer vision. So previously it was, say, the convolutional neural network was this really exciting architecture that had this spatial prior in the convolutional filters that was advancing computer vision crazy fast, and now it's transformers. So transformers are, they've achieved the state of the art in image classification, object detection, and that's a theme that's probably going to continue, that transformers continue to have more successes in data domains outside of natural language processing. And then the third driver is scale. So we've seen the size of these deep neural networks are increasing rapidly. But it is worth noting that the GPT-3 model that's 175 billion parameters, and say this latest model that's people are tweeting about is titled the Switch Transformer, that describes it being a 1.6 trillion parameter model. But the Switch Transformer is an example of a mixture of experts model. So it has sparsely activated features, and it's a conditional computation machine. So it's not the same idea. I still think GPT-3, there's also a G-shard, which is something like 600 billion parameters, but that's also a conditional computation machine. It's not like the dense architecture of GPT-3, but scale is definitely a huge theme. We've seen, say, the T5 model, NVIDIA's Megatron LM, up to, say, 10 billion parameters is like almost a common size for these language models. Scale is a bit of an intimidating topic depending on your computing setup, but it's also worth noting that there has been tons of advances in compressing these large models. We have things like knowledge distillation, quantization, where we reduce the precision of the weights, and then pruning with things like the lottery ticket hypothesis, and just generally you can reduce a ton of storage in the neural network for, say, deployment by masking out a lot of the weights to zeros, and it still retains the performance somehow. So these are some of the key compression techniques. So although scale and trying to train your own billion parameter language model or image classifier or whatever it is intimidating, the compression techniques are coming a long way as well. So knowledge distillation, quantization, you have things like quant noise as an example of one paper that does this idea of quantization aware training. So there's a lot of these cool ideas like lottery ticket hypothesis from scratch is a huge area of research. We're trying to train sparse networks right from the jump so you can save a lot of computation and achieve scale without the massive cost of doing so. As we cover so many applications of deep learning, it's important to understand how deep learning interfaces with so many different data domains. So quickly, we'll go through these different examples of how text is inputted to a deep neural network, how images are represented and inputted, how electronic health records, amino acid sequences, the molecular SMILES language to encode molecules into a language that's easy to input into deep learning systems, as well as these SIR models and black box spread forecasting models. So how do inputs to deep neural networks work? In natural language processing, the strategy is to tokenize each word such that you change it from words into integer index positions. So say you have this sentence of words are tokenized, you break that up into tokens. So words might be at position 800 in our vocabulary. So we have a vocabulary where we have a word vector for all of the words that we're going to be processing. And then it's common to have an out of vocab or an unknown token that represents words that are outside of the vocab. So say, limiting it to 30,000 it's common, and it's also a huge computational cost decision. You can't have an 100,000 or just an arbitrarily large vocabulary, because now your first layer of this neural network is going to be an embedding table that is the dimension vocab size by hidden dimension of the vector. So you want to truncate this vocabulary such that this is computationally feasible. So then each index, it has an embedding vector. This is referred to as, say, the word vector embedding dimension, or also the hidden dimension of the model. So basically what you do is you concatenate these word vectors together to form a matrix that's inputted to the deep neural network for each given word sequence. So say this task was to classify the sentiment of this sentence. You'd first turn each of these words into tokens. Each of these tokens would be mapped to their index position in the embedding vector table, and then you just concatenate these vectors together to form a matrix that is inputted to a deep neural network. If you're new to deep learning, my recommendation is to start off with computer vision because it's really intuitive how this data is inputted to a deep neural network. Images are already stored as height by width by channels tensors, where it's usually RGB, so it's 3 matrices of the height by width, where it's this grid that contains the pixel value in each slot of an image. So it's common to say CFAR10 is a very popular data set that is 32 by 32 by 3 referring to RGB. So in each of these red, green, blue channels, you have a 32 by 32 matrix that stores the pixel intensity of each value that represents this digital image. So this height by width trade-off is the resolution of the image. And this is a huge trade-off between image quality and then storage size. So CFAR10, if you visualize these images, they're blurry. I mean, they're really small images. They're 32 by 32 pixels. Compared to, say, like a high resolution image, like 4K or anything is usually like 1,000 by 1,000. It's not like a perfect square usually in these images, but it's usually like 1,000 by 1,000, somewhere in that ballpark, compared to 32 by 32. And the reason that CFAR10 is so small is because this saves computation, because it's a smaller matrix. It's the same idea as the vocabulary size with natural language processing, where we limit the vocabulary size and we limit the input resolution of images because it saves a lot of computation. But with that said, it's pretty straightforward how you take this input tensor that represents each image, and it's called a tensor because now it's 3 dimensions. It's 3 matrices of height by width pixel grids. So you just input this right into a deep neural network. Computer vision is probably the most straightforward way of understanding how this works. Computer vision also has applications like 3-dimensional images, or even these like neural rendering. They have this like graph structured sparse voxels in the 3-dimensional grid. Or there's, say, video data, so it is more complex in different applications, but most applications like ImageNet and image classification, object detection, semantic segmentation, it's this pretty straightforward input of height by width by channels. As mentioned previously, we cluster together healthcare data with biochemistry data like protein structure prediction or molecular property prediction. So these are two completely different data domains to understand how they're inputted to deep neural networks. Before describing how electronic health records are processed to be inputted to deep neural networks, it might help to start with the Titanic dataset. The Titanic dataset is one of the most common ways of explaining machine learning and data science, where we have this dataset that describes all the passengers of the Titanic, and then you're predicting whether they survived or died in the Titanic crash. So you have these combination of features. This is what the important lesson of the Titanic dataset is. You have categorical variables like the passenger's class, the gender of the passenger, the age of the passenger, which is numeric, but you have these different combinations of categorical and numerical features. Numerical features would be like the price of their ticket, and then categorical features would be like what cabin they were in, whether it's cabin A, B, C, D. So you have like these one-hot encoded categories for the variables that describe the passengers on the Titanic dataset. So with electronic health records, you similarly have this combination of different types of variables that describes the patients. The most famous, popular, open, in my opinion, useful dataset to help you get started with this is Mimic3. So you have to go to physionet.org or something. It'll be linked in the description of this video, but you have to apply for access to this data set. But once you get it, you can use it to develop these applications. It's a data set of patients in the ICU. So you have a combination of categorical variables that say describe the demographic information, and then maybe you have like treatment and operation codes. And then you also have this time series numeric that are like the physiological readings of the patient in the ICU. So it's this combination of data. And the way that you can do this with deep neural networks is similar to natural language processing. You can have an embedding table for each of these categorical variables, like the different treatment or operation codes that have been applied to the patients in the ICU in this Mimic data set. And then you can have just like a raw time series model, like an LSTM or an RNN, or maybe a transformer with a sequence position embedding that processes the physiological readings of, say, like blood pressure or all this other kind of stuff that's contained in these medical record data sets. The way proteins are processed for deep neural networks are very similar to natural language processing. We have these amino acid sequences that are encoded in embedding tables that are then inputted to deep neural networks. So you have these 21 amino acids, and then they could each represent a position in this embedding table where you have 21 different slots, and then each of these slots corresponds to, say, a d-dimensional vector. It could be like a 256-dimensional vector that represents the input for each of these amino acids. that are then concatenated together to form the protein or the sequence of amino acids that are then processed in some deep neural network, some way of doing some task of whether it's predicting the structure, whether it's retrieving these similar amino acid sequences. This is known as multiple sequence alignment. Previously, it was like, I've taken a bioinformatics class where they teach you how to do dynamic programming to align these similar amino acid sequences. And the idea is that you're able to get some of these features that helps you make predictions about this amino acid by looking at its nearest neighbors, because they share a lot of properties like chemically by having the similar kind of chains of amino acids. So just the core lesson that we're trying to get at with this early stage of our presentation is understanding that these amino acids, they represent positions in an embedding table. Each of these embedding vectors are concatenated together to form a matrix input representing each protein sequence that's inputted to some deep neural network architecture. In addition to protein structure prediction, another task is molecular property prediction. Molecular property prediction works by using the SMILES encoding language. SMILES is a way of turning chemical structures into strings that are processed by deep neural networks. So we first convert some chemical structure into a string, and then it goes into a deep neural network just as if it was like a text sequence where we tokenize it and have the same kind of idea with respect to processing the SMILES language of encoding the chemical structures and then processing them in deep neural networks. So instead of trying to explain this further, I highly recommend watching this video from Data Professor on YouTube. I highly recommend subscribing to the channel as well, another really awesome channel in the deep learning, machine learning space. This video explains the quantitative structure activity relationship task, the QSAR task of predicting molecular properties of these chemicals in these data sets. So you have these molecular structures that you encode in some kind of language like SMILES, and then you use this to construct the matrix that represents each individual data instance and input it to the deep neural network, and then it performs some task like chemical property prediction. So I highly recommend taking the time to just quickly watch this. Explain in 2 minutes, machine learning for drug discovery. Really great explanation of input-output with this QSAR task. We'll explain how epidemiology can model spread forecasting by understanding the LSTM neural network. This is from Christopher Olah's blog, one of the pioneers of deep learning, who has made this great explanation that, when I took a deep learning class at Florida Atlantic University, this is how it was explained, the LSTM network, by walking through this example. So I highly recommend it if you're not familiar with recurrent neural networks. So recurrent neural networks have loops to process sequences of data. So say X0 is the amount of COVID infections 30 days ago, 29 days ago, 28 days ago, up to today. We have this sequence of processing the infections where we can have this hidden state of the neural network that is updating the hidden state as it sees this sequence of data. So the LSTM has more structure with how it updates this hidden state. It has these forget gates, update gates. I don't remember the names of all the gates, but it has this unique way of taking the previous step's hidden cell state, the new input from, say, the sequence of infections, as well as what might have been outputted at each time step. If, say, you're training the model in an autoregressive way where you want it to predict, say, time step t+1 using t and then t-1, t-2, so on. So you want to keep making these predictions to add more structure to training the model. So this is one way of doing that, and this is the LSTM architecture. So I highly recommend just looking at this blog to understand how recurrent neural networks work, and that should help you get a sense of how we can process this sequence of infection data to make predictions about the future. But we'll look further into adding more information. So say we had like a code that represented the country, and we had several different sequences, and we're processing all these features. That it's like this idea of constructing these complex neural network architectures where you chain together LSTMs that process different sequences, taking different like embedding features that are integrated into the model. All these complex architectures that can be used to do spread forecasting. The recurrent neural network would be one way to integrate prior knowledge about a sequence of data to a deep neural network. But say we wanted to use a transformer architecture rather than an LSTM. What they do is they integrate a position embedding into the sequence to do this. So in the attention is all you need paper, they use sine and cosine functions to let the model have a sense of this word came before this word and so on. So, it has this position information of how text is written where it has this left to right syntax. So just this example is how transformers have been adapted for computer vision in Google's vision transformer architecture. So you see how the image is split into grids, and then you have this embedding that tells the model this position was in slot 1 originally, 2, 3, and so on, because the attention layer is a set operation. So it has no understanding of the order of the sequence as it does this matrix multiplication, which is the attention layer. The attention layer doesn't process data as a sequence like the LSTM would. So just to quickly get a sense of how different architectures handle sequence information like black box spread forecasting or even the SIR modeling, or with contact tracing, we'll look at these graph neural networks. So let's hop into quickly what a graph convolutional network is to get a quick sense of graph neural networks and how we might process graph structured data. Throughout this presentation, we'll see graph structured data in knowledge graphs and when we're using it for drug repurposing, as well as this idea of contact tracing, which, there aren't really data sets like this, but it's just kind of an idea that maybe you could have some kind of super detailed data set like this that is graph structured and then make personalized risk infection predictions. So finally, let's describe graph structured data. We've looked at how text is processed over deep neural networks, how images and computer vision are represented, say mixes of data like the Titanic data set and electronic health records, as well as proteins, molecular properties, and sequences of data like infection cases. So now let's look at graph structured data. So this is from Thomas Kiff's blog on graph convolutional networks. I highly recommend reading Thomas Kiff's PhD dissertation thesis on deep learning with graph structured representations if you want to go deeper into this topic. I mean, there's so much out there on graph neural networks. It's one of the most interesting fields of deep learning, but let's get a sense of the basics of how this works. So our input is a graph. The way graphs are structured in computer science is as adjacency matrices. An adjacency matrix is the size of the number of variables by the number of variables, where say in a binary graph you have a 1 that denotes the edge and a 0 denotes that they're not connected. So by having a 1 and a 0, you can render these graphs and store them in matrices, which, as we've been studying through text, images, and so on, matrices are like the language of deep neural networks. You input this matrix, and then it does a series of matrix multiplications, produces some vector matrix or single scalar output. So you construct an adjacency matrix, and then you also commonly have a feature matrix that goes in the input layer. So say this is a citation graph where this paper is cited by this paper, is cited by this paper, and so on. Like later on, we'll look at the SciCite in literature mining graph where they have this kind of relation information. You would combine the adjacency matrix with the features that describe the like text of the paper. So now let's get into the more interesting thing, which is the graph convolution. So we'll start off by describing a convolution in the convolutional neural network used for, say, ImageNet. So you could think of an image as being a regular graph or not a regular graph, but as a graph where you have this structure where you have the pixels connected to its neighbors in that grid structure. So in the case of images, the convolutional filter applies to this local 3x3 neighborhood, but you could just slide it across because it's all connected in that structure of having these pixel grids. Whereas within graphs, you can't just slide this kernel across because it's sparsely connected like this. So rather what you do is you apply this propagation of the features, this local convolutional kernel, only to a node and its neighbors. So at this time step, this node in the graph is going to send information in the form of the convolutional feature extraction to these neighbors. So it's a message passing network similar to convolutions in images that works by having this local feature aggregation where, say, this node sends a message to this node at layer 1, and then at layer 2, this node sends it further to this node and this node and this node, and then at layer 3, this node was sent to this node. So that's how message passing works in these graph convolutional networks. But what we need to understand for the sake of where we're at in our presentation is how you have a graph structured data, adjacency matrix, and input this to our deep neural network processing machine. I hope from that explanation it was clear how we construct matrices that represent each of these different data domains, and then we all can input this into these matrix multiplication processing machines that are our deep neural network. So medical images, we have these matrices of height by width by RGB, or say just by grayscale, where we just have a matrix of height by width pixel values. Protein structure prediction, where we have these amino acid vector encodings, and spread forecasting, where we have the sequence of cases that we can also represent as, say, a vector of the sequence of cases, or maybe matrices where we're integrating the sequence information from different regions and fusing together these features, as we'll describe later in the presentation. But the transformer, it can process all these different data domains once they've been properly prepared as an input to this deep neural network architecture. We'll begin our coverage of the applications for COVID-19 with deep learning by starting with natural language processing. We'll review scientific literature mining, knowledge graph construction, misinformation detection, and public sentiment analysis. Before further describing each of these applications, let's take a quick example of the GLUE benchmark as an example of what NLP has, say, solved, or what it achieves really high performance. Later in the presentation, we'll discuss generalization metrics and maybe some issues with declaring that a task has been solved by deep learning. But this is the GLUE benchmark, and it was originally designed as a set of 10 tasks to stress test these natural language processing models. It's supposed to be really hard for a model to be able to perform all 10 of these tasks simultaneously. But many of these models now, like the text-to-text transfer transformer, the T5 model, is able to achieve a massively high performance on these tasks. So the tasks that we have are in the GLUE benchmark, and it's also good for just describing what natural language processing is and examples of text tasks. We have single sentence tasks, like the COLA task in SST2. COLA is a case where you have a single sentence and you predict whether it's grammatically correct. And then SST is where you predict sentiment on movie reviews, like say the IMDb movie review data set is probably the most common example for people starting out with natural language processing and text classification. So these are examples of text classification tasks. These are examples of similarity and paraphrase tasks. So what you have, this is the machine reading paraphrase corpus, where you have two different paraphrases of each other, and you're classifying whether it's a paraphrase or if it's like completely unrelated. Same idea kind of with STSB and Quora question pairs. You have two examples of sentences, and you're telling whether they're paraphrases or if they're semantically similar or if they're not. So with Quora question pairs, people ask duplicate questions on this social media site called Quora, where you ask questions and they word the questions differently, and they have a massive volume. You see the cardinality of the training set, 364,000 pairs, where people are asking questions in the same way, but with different wording. So it has the same semantics, but different phrasing. And natural language processing can help you organize that by detecting semantic similarity. And then we have inference tasks. This natural language inference task is where you have first a premise and then a hypothesis, and you have to tell if they follow one another. So this is kind of a much more complex task, well, maybe not much more, but it's a more complex task than paraphrase or single sentence classification, where you have to really understand these relationships between the premise and the hypothesis. And this idea of understanding also something we can talk about later in generalization metrics, but it can solve this task with respect to this train test split of training on these examples and then being evaluated on the held out test set and achieving really high performance on that held out test set. So these are examples of what natural language processing can easily solve. And now we'll transfer into these applications for COVID-19 that in some cases share this kind of task setup, but in other cases are a bit more complex than this. Here's another really great example of a task or a benchmark in natural language processing that's being used to develop these models. SQUAD is the Stanford question answering dataset, and it contains these Wikipedia articles with human labeled questions and their answers in the text sequence. So this task is known as extractive question answering, where you have an input paragraph and then you have an input question, and you predict where in the paragraph the answer is. So if the question is the atomic number of the periodic table for oxygen, the model classifies where in this original paragraph the index position, the start-end sequence of the answer to this question is. This is the extractive question answering task, and there are two data sets, the SQUAD 2.0 and or SQUAD 1.1, where the key difference is 2.0 has questions that are unanswerable by the paragraph. So the model also has to output if the answer isn't in this paragraph. This is the extractive question answering task, where you classify the answer within the given input context, compared to abstractive question answering, where the model would say generate an answer rather than classifying where the answer is in a given input. So as you see from the SQUAD leaderboard, human performance is about 87 and 89, and now these deep neural network systems are able to perform better than humans at this task of classifying answers within these paragraphs. Scientific literature mining is one of the most exciting applications of deep learning. This is where our dataset is scientific papers, and we're trying to build information retrieval, fact verification, question answering, or summarization systems on top of this dataset. So the COVID-19 pandemic had tons of research has been published about it. This COVID-19 dataset, sourced by many institutions, such as the Allen Institute, the National Library of Medicine, and others, they have over 128,000 papers. Now I think it's over 140,000 papers of all these scientific papers written about COVID-19 and anything that might be relevant. So no single person or group or team could be expected to sort through this massive volume of scientific information. So what we need to do is build these natural language processing information mining systems that can extract the important information from this and help us make progress moving forward with processing this information and developing hypotheses and experiments from this literature. So here are some of the popular data sets that have been developed. The COVID-19 dataset is an example of, say, a massive unlabeled dataset of just a raw dump of all these papers. Trek COVID is an annotated dataset to test the evaluation of information retrieval systems. And then COVID QA is a question answering dataset similar to the SQUAD benchmark that's been annotated by biomedical experts. But again, it's a problem of, as we'll discuss later, learning from limited labeled data sets. You only have 124 annotated question answer pairs, so it's going to be tricky to fit one of these gigantic deep neural networks on such a small data set. This article in Nature describes one of which is, in my opinion, the most exciting development in scientific literature mining. This describes the Allen Institute's TLDR model, where it's doing abstractive summarization of research papers. So this data set was constructed by using the openreview.net platform, which I think is where people submit ICLR papers. And the way this interface works is that the authors write a short TLDR about their paper, and then also the reviewers of the paper write a quick summary of it as well. So this was used to bootstrap a data set to train these summarization models to summarize these papers. So it's been integrated into the Semantic Scholar search engine, where it's now doing deep learning generated TLDRs for these papers. So you have this summarization task where you have this data set of summaries and then the papers, and then you're using it to generalize into new papers and write new summaries. So it's a really exciting case of using these scientific literature mining systems to produce a better way of mining this enormous amount of literature. So particularly something I've become familiar with is trying to keep up with the deep learning literature, where you have just maybe like 50 papers are published every day, or maybe even more than that. But it's so much to try to keep track of. And that's why these mining systems are so exciting, to try to help us summarize the newest advances and keep up with the information overload better. So I think personally that this TLDR data set, also there's the archive data set, I think more advances will be made using these kinds of data sets because it's more intuitive for the developers of deep learning systems compared to, say, COVID-19 or the PubMed paper dumps, because it's hard to have specific subject matter expertise in both biochemistry papers as well as, say, someone who's capable of building these cutting-edge natural language processing systems. So there'll probably be a lot of interplay between real biochemical experts as they build these systems with the deep learning engineers. But I think that mining machine learning papers will be more intuitive and easier for people who build these systems to get a sense of how well the system's working. Before describing how the deep neural network architectures are performing these scientific literature mining tasks, this is an example of how the dataset is constructed, in this case for the Trek COVID dataset. They have this annotation interface in order to label this dataset to evaluate information retrieval systems. So in this case, we have a query, and then we retrieve some document that's supposed to be informative based on the query, and then this is the annotation interface for selecting if the information retrieval system did a good job of fetching a paper that's relevant to the query. In my literature review of different deep learning systems tackling scientific literature mining tasks, this is the architecture that I thought was the most impressive. Co-search from Steve et al., these authors. The paper, like many of these papers, are linked in the description of this video if you want to check it out further. So here's a description of the system. So this is a combination of information retrieval as well as question answering and abstractive summarization. So the first idea is you have the document corpus. In this case, this is our COVID-19 dataset of scientific papers related to COVID-19. So from this, the first task is to form atomic units of the papers. So we have to construct a sequence length that describes each of these papers. So we might split this up into different paragraphs. We might say just use the abstracts of the papers, the results section, or something like this to form the atomic units of each paper. And also paper could be split into multiple atomic units. If, say, we just want to arbitrarily decide that 200 tokens is a sequence length to divide the papers into. So we have this document corpus, and we've constructed it into each atomic unit that is going to represent some information, some input to be processed by our information retrieval system. So we could have paragraphs or image captions as another example, and now we process this with different feature extractors for the deep learning system. So first we use BM25 and term frequency, inverse document frequency feature vectors for the different paragraphs. So these are the features that have been used in machine learning to describe data. So similar to how in computer vision before deep neural networks were used in AlexNet, they had things like the color histograms, these different ways of extracting features that describes high-dimensional image data. So TF-IDF and BM25, these are ways of forming feature vectors from these documents without relying on parametric encodings like deep neural networks. So now let's discuss this other way of extracting features that describe each of these atomic units for the documents, the Siamese sentence BERT architecture. So the difference between SBERT and BERT is that BERT would have to do pairwise comparisons of similarity. So say when you're doing the Cora question pair task BERT would have to take in two different questions and then process them in this pairwise classification or pairwise regression task. And then say you're doing that comparison with a massive document, you'd have to do, an enormous amount of comparisons to process it. Compared to Siamese BERT, which just forms one encoding for each of the documents, and then you use something like the FAISS, FAISS vector search engine, or these different libraries that have been used to do GPU acceleration for vector similarity search, where you have a vector encoding of each of these documents, and it's easier to do similarity than, say, doing pairwise classification or regression. So that's how you encode each of these documents using a combination of TF-IDF and BM25 feature vectors, as well as the encodings from the Siamese BERT architecture. And there are many ways of training these Siamese BERT models, like, say, contrastive self-supervised learning. The first half of the co-search system constructs the index of these documents. So all these documents have been split apart into the atomic units, and then they've been encoded such that they're now vectors representing all of this information. So now we move into the retrieval system. So we take a new query like, will vitamin D help lessen symptoms of COVID-19? And we encode that query using the same feature encodings of the text as how we encoded our documents. So now we encode this query into a text vector similar to the indexes, the vectors that have been used to represent the information in our document corpus. And now we do a k-nearest neighbors lookup between the vector that represents the query and its nearest neighbors in the index. So now that we've retrieved this information from our document corpus by using this vector similarity search, we use the retrieved documents as input to three different tasks. We have re-ranking, and then we have question answering and abstractive summarization. So in information retrieval, there's usually two halves, or it's usually a multi-stage system where you have different levels of retrieval and then re-ranking. And the key difference between retrieval and re-ranking is that re-ranking are usually like more computationally expensive models. Now you might use something like the BERT pairwise comparison model or something like that to rank the relevance of, say, a large set of retrieved documents from the more coarse-grained step of indexing. So we also feed this as input to a question answering model, and say this could be like a squad system where it's trying to classify an answer within the documents, or it could be using the documents as input to abstractively generate a novel answer to the question or a novel summary of the information pertaining to the query. So as we're reviewing these different deep learning systems and papers that have come out on the scientific literature mining task, it's noteworthy that they vary in these subtle ways. So the COVID-19 paper uses sequence-to-sequence re-ranking. So how do we particularly implement this re-ranking? Are we doing pairwise comparisons? Or in this case, what they're doing is they're having a sequence-to-sequence model, the mono T5 model, that is going to take in the query, the document, and then classify whether, or output something, whether it's relevant. So T5 stands for the text-to-text transfer transformer. It's a model that's developed to do text input and text output that unifies all these classification and regression tasks. So rather than outputting some classification logic vector, it's going to output pure text that represents its response to the input. So it's going to be outputting a score on how relevant it thinks each of these documents are, and then you organize that for the output documents in the re-ranking step. So it was trained by using this MS-Marco dataset. The MS-Marco dataset is 8.8 million passages that have been obtained from the Bing search engine, corresponding to 1 million unique queries. So in SLEDGE and CARE-COVID, similar to this MS-Marco dataset, they're using different datasets to train these models to do re-ranking. So how are we training these models to do re-ranking? We've seen previously how this is one way of constructing a dataset for information retrieval evaluation, say having some kind of supervised evaluation of these systems. And in the COVID QA, it only has 124 pairs. So you need some way of bootstrapping data to perform this task. So SLEDGE is using the SciBERT model, and CARE-COVID is using BioBERT fine-tuned on Squad. So these are different SciBERT and BioBERT, basically referring to different paper corpuses that have been used to pre-train these models with the mass language modeling task. So some of the key differences are just in these subtleties in which they implement these different re-ranking or different kind of systems of encoding this vector representations, as well as the data sets that are used for auxiliary self-supervised learning when you're seeding the representations of these deep neural networks. The next topic is the automated construction of knowledge graphs using deep learning. So we have these large corpuses of scientific papers. How can we extract the factual information of relations between nodes in these graphs? So say we have the 2019 nCoV virus, and then we have a relation like binds to the ACE2 membrane protein, and then endocytosis is involved in the ACE2. How we have these different relations that connect these nodes in our data set of this information from the scientific papers. So how can we use deep learning to extract these node relationships automatically from these graphs, from these data sets, and then produce these graphs that we can use that are interpretable and we can query them. Biomedical experts can query them, more importantly, and we can use them to find things like drug repurposing, or trying to find a drug that's been approved, like this drug, in order to see and do these queries that require significant subject matter expertise, to use these knowledge graphs to the advantage of finding drugs to be repurposed. In addition to knowledge graphs that store information about relations between protein-protein interactions or drug-target interactions and things like this, we also might want to structure the scientific literature mining task as a knowledge graph. So a great example of this is SciSite. SciSite has relations between, say, this paper cites this paper, or this is from the same institution as this paper is. It has all these different edges. See, it's not just 1-0 binary relations. It has several different kind of relations that relate how these papers are related. So it might have more. It might be more useful for these scientific literature mining tasks to also be embedded in the context of which science is produced, where we have these authors, institutions, and how they're connected with each other in these graphs, authored by, affiliated with, associated concept between, say, contrastive learning and then auxiliary task prediction. They're both associated through this concept of self-supervised learning. And we have all these other ideas where different concepts in science are related through a broader concept or topic. And they explicitly construct this graph data that makes it maybe more interpretable, as well as applicable for, say, graph neural networks or something like that. COVID-19 was such a chaotic new event, and people were so scared of it, and everyone wants to know what's true and what do I need to watch out for. All this new information with respect to how should we react to this COVID-19 disease and coronavirus. Misinformation detection is one of the most critical applications in the COVID-19 response, where we're trying to find out what's true, what's a rumor, what's false with respect to all the information about COVID-19. So here are some of the key data sets towards developing fact verification applications. SciFact is my favorite. It's an extension on the Core-19 dataset from the Allen Institute, where they have 1,400 examples of scientific claims and then retrieved evidence that either supports or refutes that claim. Fever is an example of the more general case of fact verification, where you say just have any kind of claim, and I think you use Wikipedia data as supporting evidence for the same task of, does this evidence support or refute this scientific claim? These are other examples surveyed in the paper where you can treat this as a multi-label classification task. So you have different kinds of misinformation that's being spread on, say, social networks like Twitter, and you label particularly what the harm might be in these classification, in this different misinformation. So is it just misinformative? Is it informative? Is it irrelevant? No need to flag it and process it for COVID-19 information, or other things like UCI. They have these biomedical experts where people could be spreading information that is very dangerous to believe is true. In addition to publishing the SciFact dataset, the Allen Institute for AI has also been organizing the SciFever shared task at this conference, having the leaderboard page and this website where they've trained baseline models, and you can try out different claims and see how the SciFact system responds to different claims you might have about COVID-19. So in this case, you're asking the scientific claim, hypertension is a common comorbidity seen in COVID-19 patients. So now the model has identified that there's 12 papers that support this claim. So it's taking different cases from the scientific data set of Core-19, and it's classifying if it supports or refutes the scientific claim of hypertension is a common comorbidity seen in COVID-19 patients. So the SciFact demo, you can check this out. It's going to be linked in the description of this video. One of, I think, the most important applications of natural language processing and fact verification will be more applicable outside of just COVID-19 as well. Another really interesting application for natural language processing for COVID-19 response is public sentiment analysis. We have datasets like Twitter datasets that have been used to train models like COVID Twitter BERT in order to see how the public sentiment is reacting to these different events related to COVID-19, information, vaccine development, and all this new stuff that comes out with respect to COVID-19, and having a sense of how people are reacting to this. So in addition to kind of like broad scale surveys on Twitter, it would also be useful to design interfaces for social scientists to use free text survey responses and then categorize these into broad semantic labels like positive, negative, or even more detailed like scared, optimistic, these kinds of things. So it's useful to not only train deep learning models that do public sentiment analysis and then publish a paper where we ablate these slight differences and achieve some high performance on the test set, but to integrate this into free text survey response tools that social scientists who are more equipped and educated on how to use this kind of analysis can use to integrate the deep learning tools with the existing tools for public sentiment analysis. Computer vision has seen some of the most dramatic successes of deep learning. These include things like how StyleGAN can generate photorealistic faces, how GAUGAN can synthesize photorealistic landscapes from pixel maps, and all these other artistic applications, as well as object detection, semantic segmentation, progress in self-driving cars, and we're going to survey these applications in COVID-19, including medical image analysis, ambient intelligence, and the role of computer vision and robotics in vision-based robotic systems. Our coverage of medical image analysis is focused on taking these images and classifying them into different kinds of either just viral-induced pneumonia or particularly COVID pneumonia, as well as the prognosis or the progression of the COVID symptoms in some of these latest papers, such as a recent study from Facebook AI and NYU, where they look at the medical images across a 96-hour window for these chest x-rays and see how this progresses. So some of the key data sets, or before we even get into that, there are other ideas in medical image analysis like semantic segmentation that are more designed for interpretability and producing something that's useful for the doctor to make the diagnosis and just provides more annotation on the medical image, as well as different deep learning systems that are used to control the parameters of achieving the medical image in the first place. So in COVID-19, ideally you'd want to have contact-free medical imaging where the doctor or the nurse doesn't have to come into contact with the potentially COVID-infected patient, and you could still have the right parameters of the medical imaging system. So those are some other examples of how deep learning could be used for medical imaging, but here we're particularly focused on the image classification problem with respect to these medical images. So some of the key data sets are the COVID-X data set. That's it's accessible on GitHub. It's an example of these labeled pairs or of the COVID pneumonia compared to either a healthy lung image or some other viral-induced pneumonia. And then CheckSpurt, which isn't COVID cases, but is a very large data set of chest x-rays. And as we discussed in the theme of this self-supervised learning, is self-supervised learning is much more useful when you have in-domain data for the massive unlabeled data set compared to just using, say, ImageNet. So this paper, Transfusion, it shows that ImageNet pre-training is not that useful. But if you're doing in-domain data like CheckSpurt, that is going to be really useful. And that's a lesson from Don't Stop Pre-Training, which is one of the best papers at ACL showing this lesson with respect to natural language processing. So another huge theme in medical image analysis is that contrastive self-supervised learning is crushing it. We're seeing papers like implementing MoCo and SimClear to do this self-supervised learning with these auxiliary data sets, because we do have a small labeled data set in the COVID-X case. Before getting into some of the works that have been surveyed in our paper, this is the cutting edge that came out after our paper, January 15th. This is the latest survey study from Facebook and NYU, where they're looking at the progression of the chest x-rays over this window. So you can see in this animation of how their system works, that they have these medical images, they encode them, and this encoder is trained using contrastive self-supervised learning. And then from this vector representation, they do the oxygen prediction over this 96-hour window. So they're predicting the progression of the disease by using the representations of the medical images, and then they have this labeled data set of the oxygen readings as this progresses. So the key role here is the use of the momentum contrastive learning algorithm for contrastive representation learning on this big data set of CheckSpurt, and then it's transferred to their much smaller data set of these chest x-rays. So you see mentioned here, they have 26,000 of these x-ray images that are taken from 4,914 unique patients, and it's done over this window of 24, 48, 72, and 96 hours as they take each image and then the reading of the ICU bed predictions, as well as this oxygen reading in the first example. So this is the most cutting edge example, and I will get into more of the foundation of the papers that originally started implementing MoCo contrastive learning for representation learning on medical images and applying this to COVID-19 image classification. So this paper, MoCo Pre-Training Improves Representation and Transferability of Chest X-ray Models, lays this foundation of, in this case, they start out with ImageNet and they compare how ImageNet works with the representations learned from doing contrastive learning with the CheckSpurt dataset, and then eventually fine-tuning it for other kinds of lung or chest X-ray imaging tasks. So I'm not sure if this paper particularly focuses on COVID-19, but it lays this kind of foundation of in-domain data for the self-supervised pre-training, and particularly also this is combining it in a semi-supervised loop. So semi-supervised, I might have left that out of the learning variants, and that was a mistake. Semi-supervised learning is another key learning variant where you're integrating steps of supervised learning and self-supervised learning or other kinds of ways to propagate the information from the smaller labeled set with the massive unlabeled set. So that was a big blunder in listing the learning variants, but hopefully now it's made up and you understand the semi-supervised learning paradigm is another huge role in learning task variants and integrating supervised and self-supervised learning. It's not well diagrammed in this picture, but hopefully just my quick description of it makes it clear that semi-supervised learning is about integrating supervised updates with self-supervised updates. Our next surveyed example of using contrastive representation learning for medical image analysis is similar to the recent breakthrough from OpenAI on multimodal learning and combining image and text representation learning. So CLIP from OpenAI is about grabbing this enormous data set by looking at all the images on the internet and their corresponding text captions and using this to form the contrastive learning pairs, where the positive pairs are the text caption and the corresponding image, and the negative pairs are all the other text captions and all the other images. So it has this matrix of representation similarity that bridges the text information with the image information and has led to these amazing advances, particularly in zero-shot image classification. And we're also seeing things are being tweeted out, not formal papers, but where they use things like you generate a bunch of samples from something like a big GAN, and then you use CLIP to filter through the generative model. So a huge advancement for generative data augmentation is likely on the horizon with this kind of advancement. But for our sake, what we're looking at is the bridging between images and text for representation learning, and particularly integrated in this contrastive learning framework. So what we have with these medical images is doctors often quickly describe what happened or how they interpret the image. So we have these text descriptions like radiograph shows pleural effusion in the right lobe, these kinds of text descriptions from doctors who know what they're looking at. And then you align these pairs by doing this image and text contrastive learning framework. And this is leading to huge advances in the representations that are then fine-tuned for classification tasks. Illuminating the dark spaces of healthcare with ambient intelligence describes many different ways that computer vision could help to collect more data and improve operations in hospitals by doing things like monitoring activities in ICUs to avoid ICU-acquired weaknesses, all the way into surgery training, hand washing detection, and a long list of applications mentioned in this survey paper about how computer vision could improve operations in hospitals. This image showcases different sensors that could be planted in the hospitals to collect more data and train more deep neural networks to perform different kinds of tasks, highlighted in this column this row as uses. So we have the camera, the depth sensor, thermal sensors, radio sensors, and acoustic sensors that can be used to collect more information for downstream tasks like equipment safety or event detection. This is another example of different technical approaches to each of these sub-challenges within challenges of things like behavior recognition in complex scenes, like when we're looking at behavior of ICU monitoring, or these other kinds of things like learning with big data and rare events, particularly looking at, say, anomaly detection in these data sets. So say we have these acoustic sensors, or we're looking for event detection particularly. This is like a anomaly detection is what they call this kind of task in the literature, where you're looking for this out of distribution kind of event to happen throughout this continuous monitoring of the image stream. Next, we'll look at how vision-based robotics can impact COVID-19. I've highlighted this image of Covariant.ai because I believe it's one of the most cutting-edge startups looking to implement vision-based robotics. These are some of the key research areas that I think will have a huge impact on vision-based robotics. The first of which is model-based reinforcement learning. Model-based reinforcement learning describes where the agent is learning a model of its environment, such that it has a generative model of predicting the next state given a state-action pair. So by learning this transition and then having a reliable model to predict trajectories of state action, the model can now do planning. It can plan in its world model, which is what Mu0 uses in order to be so good at chess and shogi and all these games, because it has this model of the game and then it can use the model to plan different trajectories. Similarly, robotic systems will be able to plan different trajectories for performing tasks like folding a towel or sorting objects, or in this case, solving a Rubik's Cube with a robotic hand. Another interesting area is offline reinforcement learning and learning from demonstrations. These demonstrations could be from humans controlling the robot. In some cases, they use a cycloGAN to even translate from human demonstrations into what it would look like if the robotic arm was doing it. And all these other things of maybe other robots have demonstrated how to do the task. So they have this data set called RoboNet, where they have tons of these examples of different tasks, and they're trying to use that to learn representations for reinforcement learning control. But key to the offline reinforcement learning task is that the policy isn't used to collect the data. So it's a much different paradigm for reinforcement learning where you don't actually use the policy to collect data. Rather, it has to infer the sparse reward from a sequence of state action decisions from previously collected data. So another theme in vision-based robotics is contrastive representation learning. So this paper, Curl, in addition to processing the visual input to do the state action mapping, it also constructs an auxiliary task in a multitask learning framework where it does the contrastive learning, and thus it forms a better representation for Q learning or the reinforcement learning control task. So the last idea is automatic domain randomization. This is what's used in OpenAI's paper, Solving Rubik's Cube with a Robot Hand. In this case, they have a simulated environment where they can control the parameters of the vision parameters like the lighting and the different colors on the Rubik's Cube, as well as the physics parameters like the friction, the size of the cube, the size of the robotic hand, and all these other variables that render the environment in this simulation to real transfer. So the way that they're able to transfer from simulation to the real world, sim to real, is by doing automatic domain randomization. So the algorithm is training the reinforced learning policy in such a diverse set of environments that now it can generalize to the real world as if it was just another configuration of the environments, of the parameters that rendered all these different environments. So it's kind of like an idea of data augmentation, this idea of having, or maybe also procedural generation, controlling these parameters that render the training data such that you can enable better generalization. Here's a collection of some of my favorite advances in deep learning robotics on the Berkeley AI Research blog. This is an example of how they're training these models to do things like folding cloth. You can see many different examples of how they do model-free learning without demonstration, model-free learning with simulated demonstrations. It's a collection of a summary of all these different research papers that are grouped together into this blog post, showing how something like this is possible. A really amazing case of learning to fold this towel with a robotic arm. Another great blog post is Ingredients of Real-World Robotic Reinforcement Learning. This blog post discusses exactly what makes reinforcement learning for robotics so difficult, particular challenges that arise like no reset mechanism. For example, when the model fails, how do you reset back to, say, state 0 in which you want to roll out these trajectories? It's not like OpenAI Gym where you can just reset the environment and then have another trajectory of learning experience. This is the RoboNet dataset that was previously mentioned. They're collecting this giant dataset of demonstrations to try to learn in the offline reinforcement learning setting where they have these 15 million video frames of demonstrations. And then how can you learn a policy from this without actually getting to use that policy to collect its own data? And then another case in the setting of model-based reinforcement learning is Plan to Explore, which is simultaneously combining the idea of model building with the exploration-exploitation trade-off and how models should explore in order to build up its world model and then have this world model that it can do trajectory planning in. So these are all some really exciting advances combining deep learning and robotics. And I've chosen vision-based robotics because a lot of these systems have some kind of visual input that they're using to process the state of the environment and make these state to action decisions. Now we'll explore applications of deep learning for life sciences for COVID-19. These include precision diagnostics, protein structure prediction to get the structure of the shell proteins of the coronavirus, as well as drug repurposing to avoid the costly and timely process of trying to bring a new drug to market, rather trying to find an existing drug that might help combat the spread and infection of the virus. This image provides a very high-level overview of what we're after with precision medicine and precision diagnostics. We want to use all this information about patients like the genome, proteome, all these things in addition to, say, their entire electronic record collection over their lifetime, family history, all this kind of data to make a more informed prediction by having these large data sets that we can mine and look for these kind of correlations and maybe form causal hypotheses by mining these massive data sets. So it's kind of a cartoon illustration describing this idea that we want to have all these different data sources to describe these patients to make better predictions on COVID-19 or more generally improving healthcare for other kinds of diseases. Here's a rough description of how the RT-PCR testing for COVID-19, the reverse transcription polymerase chain reaction test works. So we're trying to find this gene of interest within the RNA. So we take some RNA doing something like where they have the nasal swab that goes deep into your nose and then they get out some of this RNA. And from what they do is they use these enzymes that are going to bind to it and then amplify the DNA such that it's a lot larger than the original sample. So within this much larger sample, they're able to sequence it and try to classify the viral RNA within the sample that they took from the nasal swab. So they're trying to amplify this, and then they use that to try to have a better signal to detect it within the sequence once it's been amplified. I think it's like 10 to 20 times, something like. They really heavily magnify the original sample using these enzymes that hook on, and then they detach it, bind another messenger RNA to copy it again, and then break it again, copy it again to amplify it to have a much larger sequence of RNA. This amplification can be a bit noisy with how much information is in this sequence. So what this study does, cited in the paper, is they're trying to train classification models on this data set to get a better sense of how to use deep learning, machine learning models to classify the presence of the COVID-19 virus within this amplified sequence, giving a data set of these amplified sequences and then the resulting diagnosis. An empirical study of representation learning for reinforcement learning in healthcare is a really great paper describing the use of offline reinforcement learning for precision diagnosis and precision control over the treatment once we have these cases, and how are we administering different kinds of treatments and operations within hospitals and more generally outside of COVID-19 as well. Particularly, they're working with this MIMIC-3 data set. And as mentioned earlier, this is the most popular / useful. It's open data set of, in this case, it's ICU data and the treatments that are applied in the ICU. So why is this an offline reinforcement learning problem? The reason it's offline RL is because we can't have a policy that's like a doctor reinforcement learning agent that is going to sample its own data as it's initially being trained. We need it to already be pretty good. You don't want to be having it experimenting with new patients to sample its own data. So it needs to be learning from these previously collected interactions of the doctor and the patients in order to start bootstrapping representation. And a really cool thing about this is then it can forecast trajectories into the future, because it can make these predictions of, say, model-based reinforcement learning, where it can predict what will happen to patient state as you make different treatment actions. So this paper is describing different techniques for representation learning with this data. So similarly to Curl is a paper in robotic reinforcement learning that uses an auxiliary contrastive learning task to improve the representation of pixel inputs such that you have a better representation to do Q learning for robotic control, like solving a Rubik's Cube or whatever control task is being performed. So in this case, they're looking for auxiliary tasks to improve the representation of patient state. So one way they do this is by trying to predict the patient demographic information from the state, doing things like the generative reconstruction tasks. So things like autoencoders or even like GANs or autoregressive models, you can, if any kind of data, you can construct some kind of generative auxiliary task where you just mask out the data and then predict what's been masked out. So these are a couple of the strategies that are explored in this paper in order to try to learn a better representation of the patient state, such that you can train better policies from these demonstrations of the doctors interacting with these patients in the ICUs in the MIMIC-3 data set. But this should hopefully be able to really improve control, like in healthcare generally, but particularly also with COVID-19, where we are starting to have these data sets. I don't think there are many open data sets like MIMIC-3 for COVID patients, but we can see how we can use these logged interactions to bootstrap reinforcement learning agents that can do things like model-based reinforcement learning and then simulate potential trajectories with different potential treatment sequences. On August 4th, DeepMind published this blog post, Computational Predictions of Protein Structures Associated with COVID-19. This blog post documents using the AlphaFold system to predict the shell proteins on SARS-CoV-2, as well as other things like they describe here the ORF3A protein, all these kinds of things that I know nothing about, but somebody who knows about proteins would be more informative about. But let's get back to describing the latest advancement, the AlphaFold 2 system, and how this uses deep learning. Since deploying the AlphaFold 1 system, that was a ResNet architecture that predicted the pairwise distances as well. So having this additional structure in the loss function and using this deep residual neural network were a couple of the advances that caused AlphaFold 1 to be so successful. But now AlphaFold 2 is much more successful than AlphaFold 1, and particularly because it's using these graph neural network transformers to predict these protein structures directly in three-dimensional space. So they don't have a formal research paper that exactly describes the system, so I'm just guessing at how it works based on this diagram in the blog post describing AlphaFold 2. So in AlphaFold 2, they have the input is the amino acid sequence of this protein. Then they have the multiple sequence alignment embedding, which is kind of like an information retrieval problem where you're looking for the nearest neighbors that align with this amino acid sequence, because this provides additional features that'll help us guess. And we do, as we have this training data set using this information, these have labeled pairs of 3D structures, and we use that to improve our representation on this given amino acid sequence with its nearest neighbors and information we have about the structure of these neighbors to make the next prediction. So it has layers of the transformer neural network applying attention layers to this kind of model. And then at the output, it has this graph structure of a three-dimensional structure. So the idea behind this is you're predicting a three-dimensional structure where the data is height by width by depth now. And when you do that, you don't want to have dense voxels in each of these slots. So voxels typically range from -400 to 1,000 or something like that with respect to the intensity or how you store each individual value, kind of like the pixel value in an RGB image. And you don't want to have a dense voxel representation of this. Rather, you want to have this sparse activation where you structure it like a graph and you have edges that connect the different voxels in this three-dimensional volume. So that's one detail about how they represent the 3D structure probably, and just kind of guessing at it. Obviously, it's not a complete research paper that describes exactly how the system works. But another interesting thing to note about this is the semi-supervised learning problem. They denote how they have 170,000 protein sequences that have been labeled with the experimentally verified structure. That's the way that this CASP13 competition works, is that they have these new verified structures and they don't release them yet. They hold on to them to use as the test set with each, I don't know if it's an annual competition, but they have iterations of this competition where they release the new structures to be predicted by the different protein structure prediction systems. But in addition to this, from the protein data bank, they also have something like millions of protein structures that occur in the wild from the UniProt data set. So they have this semi-supervised learning problem of having labeled protein structures as well as just raw amino acid sequences that occur in nature and have been filtered out through evolution. So hopefully this is a decent overview of the AlphaFold 2 system. I highly recommend videos from, say, Yannick Kilcher that go into further detail about how this works. The next application for deep learning in COVID-19 that we survey is drug repurposing. It's very expensive and time-consuming to develop an entirely new drug to treat COVID-19. So the more practical solution is to repurpose an existing approved drug that, in addition to being approved in the clinical trial process, it also probably has some kind of supply chain infrastructure to distribute these drugs. So how do we find these new drugs? So it's a scientific literature mining task, but differently from, say, the co-search system of indexing and then passing these documents for re-ranking or question answering summarization, it's much more common to use the knowledge graphs because we need the domain expertise to query the graphs. We just want to kind of help construct these graphs and then pass it off to someone who actually has the domain information to know what to look for with respect to these drugs. So this is an example of the benevolent AI knowledge graph shown earlier, where these kind of queries like knowing this inhibition and potential promoting this, which could be a challenging side effect, and this does this. This is all things that I don't think deep learning engineers are going to be able to do, but this collaboration with doctors and people who do this kind of thing is going to be useful through this knowledge graph handoff, where we construct the knowledge graphs using maybe the heuristically labeled weakly supervised relation task. We have these ways of constructing these knowledge graphs, and then the domain experts can mine it. So I think this is called network medicine. I could be wrong exactly using this terminology to describe these kind of protein-protein interaction networks, drug target networks, different ways of structuring this kind of data for the biochemical mining. So one strategy that could be interesting is the use of graph neural networks, deep walk, and then particularly I read this paper, rotate E is what they call the algorithm, to try to maybe propose. So you have tasks in graphs like, say, link prediction, where you're trying to predict a link that doesn't already exist in the data set, or you're trying to do, say, node classification, or maybe even like subgraph classification. All these different tasks that maybe graph neural networks are prepared to facilitate in querying these knowledge graphs and the handoff between deep learning engineers to medical researchers and doctors. If you want to learn more about drug repurposing, I highly recommend this survey paper on artificial intelligence and COVID-19 drug repurposing. Among many things, they discuss many different surveyed applications of using, say, graph neural networks, things like deep walk, to mine these knowledge graphs and propose potential drug repurposing candidates. Spread forecasting is one of the most important applications to combat COVID-19. This is useful for applications like resource allocation and overall getting a sense of the spread of the virus. We'll discuss 3 different kinds of applications. Black box spread forecasting that kind of treats this like a sequence of numbers and maybe also integrates nearby region information to get a little more structure to this sequence of numbers of infections. SIR modeling will add more structure by particularly dividing the population into susceptible, infected, and recovered populations, maybe also SEIR models adding in the exposed population as well. And we'll see how we also can use this division of populations to try to use a neural network to predict the quarantine strength, which is time varying, probably not a consistent quarantine strength in each of these different regions. Then contact tracing is a more ambitious idea of having this super detailed information of who's coming into contact with who, exactly how far have they been from each other. Maybe was there a cough, some kind of event that might have caused a transfer of the virus. This kind of extremely detailed data that might also add further structure to these models and provide not only personalized risk infection, but much better forecasting at the population level with the more detailed the data is. With respect to black box forecasting, we're referring to looking at graphs like this. So this is what I've been checking on every day, the daily new cases in Florida. The idea would be to use this kind of data, maybe also using nearby states like Georgia to try to get more information, or even further dividing it into county level infections and then using the neighboring counties to get more information about this sequence of numbers as well. So it's using this kind of time series data to make predictions about the future in a kind of naive way of just treating it like a sequence of numbers. This paper, High COVID-Net, does exactly that. It uses the county level representations to form an overall vector embedding for the continent level representation, or country level, and then the continent level representations to use this kind of black box forecasting with respect to the daily numbers, as well as, in this case, they're looking at traveling risks. So they're looking at the inflow, meaning as people travel from one country to another, and using this to further structure the modeling of how they're setting up this sequence modeling task. So you see they have the transformer layer, LCM, vector concatenate. You're seeing this kind of like deep neural network architecture as they form this construction of different kinds of features and integrate them in late fusion, fusing the features, and these kinds of architectures that are used to process complex information in deep neural networks. SIR model solved a series of differential equations to get more information, particularly about the reproductive rate of the virus, known as the R0. So the R0 is done by taking this gamma over the sigma, or I don't know the exact equation, but some sigma over the gamma, some combination of processing these two variables that are solved by solving these differential equations where you have this information about the change in the susceptible population, change in the exposed population, and how each of these populations relate to one another in this series of differential equations. This study is looking at adding even further structure to the SIR model and introducing more fine-grained parameters for the sigma and gamma that has more information about exactly what the transmission rate is, the recovery rate with respect to different ways of treating the virus, whether you just kind of go to an ICU or if you just don't, it's undocumented, I don't know if that's in it, but these different ways of treating the transitions from susceptible to exposed to infected to recovered. So it adds more structure, adds more variables, and you can imagine using a deep neural network to solve this system of equations. Another idea to combat COVID-19 and predict the spread of it is contact tracing. This is another thing we'll discuss with respect to the limitations of deep learning and data privacy. But we could imagine these kinds of data sets that have this graph structured information about who's been near whom, exactly how far they are from each other, and then also labeling them on susceptible, exposed, infected, and recovered or removed if, unfortunately they've died from the virus. And this is integrating the SEIR models with this kind of detailed contact tracing data. So this paper is describing using graph neural networks, a reinforced learning control framework, where you're trying to prescribe what to do, quarantine, etc., for each of the individuals with the personalized risk analysis based on this kind of extremely detailed data. Now that we've described several applications of deep learning to combat COVID-19 in natural language processing, computer vision, life sciences, and epidemiology, we'll look at some limitations of deep learning that cut across all these applications. They're general limitations of using deep neural networks to fit functions with data, use self-supervised learning, all these things. They still have these kind of caveats that generally restrict performance. The first of which is interpretability, then generalization metrics, the challenge of learning from limited labeled data, and the issue of data privacy. Interpretability is really important for communicating the predictions of deep neural networks with subject matter experts. We've seen things like drug repurposing, precision diagnosis, or even public sentiment analysis, where we want to have someone who's more knowledgeable about the specific application area to use the deep neural network. It's not up to the deep neural network to just perform the whole task. We want it to produce some kind of output artifact that's handed off to a subject matter expert. So the question then is, are neural networks black boxes? Can we do anything to get a sense of what caused it to make the prediction? Can we inspect the neural network to see where it might fail when it goes out of distribution a little bit? And the answer to this, I think, is increasingly yes. And we see things like OpenAI Microscope, Deep Dream, Dream to Distill. These are all examples of optimizing features that will particularly activate a group of neurons. So you would take an image and say you want to activate a subset of neurons. You'd apply this gradient to construct the image that maximally activates these neurons. And in Deep Dream, they use this to construct these cool images, but it also can be useful for getting a sense of what features the neural network is looking at. So the next thing is representation analysis. We have the product of deep learning is to produce these vectors that represent high-dimensional data. So one idea is to use TSNE, the unsupervised learning, once you already have these representations, to visualize them in a lower dimensional space. So say you have the co-search system, it produces these 512 dimensional vectors that represent the documents in Core 19. Now you want to reduce that to 2 or 3 dimensions so a human can look through it and inspect the difference between the papers and how they've been encoded. So the key to this is NVIDIA has developed a software library called Rapids. And the difference in using TSNE with, say, scikit-learn to Rapids is enormous. It's a completely game-changing idea. Rapids would do TSNE in like 2 seconds compared to where scikit-learn would take like a whole day to do it. So this GPU acceleration is a huge step forward in doing this kind of low-dimensional vector representation analysis. So then we've seen papers like Lime, which we'll cover in more detail next, just a quick overview of it, where we're trying to look at the features, similar idea as this, but this is more about like images and, generating images that maximally activate neurons or convolutional filters. Lime is generally a framework for this idea of finding out what features cause a prediction. And then WT5 or YT5 is about training the text-to-text transfer transformer with an explanations dataset. So it will predict something, and then because it has this text input, text output interface, we could just ask it, why did you make this prediction? And maybe that would work if it was trained on enough data. Hopefully it's maybe more of a moonshot idea, but maybe it will work if you have enough data in a similar way that GPT-3 has so much data that it does this interesting behavior. This is the idea behind the Lime algorithm. In the paper, Why Should I Trust You? Explaining the predictions of any classifier. So similar to how in machine learning we have models like the light GBM classifier, or these decision trees where we can see the features that are the most important for making the prediction, that have the most predictive value, like when you do feature selection techniques for machine learning. We want to have some kind of framework where we can see what kind of data causes different predictions, and then have this kind of weighting where we see how these bars communicate exactly which of these words. Say in this case you have like a text classification problem. How much did each of these words influence the prediction? So this kind of information that we want to extract from deep learning. This is a high-level overview, and you can read more about the exact details of implementing Lime in this paper. This is just a quick motivation of how we want to extract the important features from the model that's been trained on these large data sets. This is the Wikipedia page for Deep Dream. Deep Dream is really famous because it produces these amazing images that have a lot of artistic value, but they can also be really useful for interpretability and helping us get a sense of what features. Say it produces a bunch of cat heads, we can get a sense of what the convolutional network is looking for, as it does something like cat versus dog classification, ImageNet classification, or in these tasks. So the way this works is you train an image classifier, then you use those features as the loss function for a generative model that's producing an image that maximally activates neurons in that pre-trained frozen feature extractor. So you use that loss function to generate from, say, random noise into an image if you're doing like a GAN framework kind of generator, or it could just be from any starting image, like an image-to-image translation problem, translate this image into something that will maximally activate the features in this frozen feature extractor. So the other idea we talked about quickly was the WT5 model for explaining prediction. So the T5 text-to-text transfer transformer, it has this unification of text input, text output that allows you to learn all these tasks simultaneously in one transformer neural network. So the idea is just to also construct a data set with explanations and then just kind of add this to the text input, text output, make this another one of the tasks that it's doing. And now maybe it could do inference where you just append explain to the task description, and then So the way this works is, say it's sentiment classification, you use it by saying sentiment, colon, and then the individual data instance, and then it'll do this prediction in text. So text input, text output. Maybe we can construct a data set of explanations and train it on that. But then again, there's these issues of things like catastrophic forgetting, continual learning. It might not be so straightforward to just construct this data set and then just append it to the data set. The next issue with respect to deep learning systems is generalization metrics. Generalization refers to how well the model is going to perform when it's being deployed in the wild, or if it's being evaluated on some test set. So we're no longer evaluating our model on how well it's fit the training data. Now we want to see how it's going to perform on new instances. So the previous approach to this was having train, validation, test data splits. You train your model in the train set, you do hyperparameter optimization with the validation set, and then you report the test set, say accuracy, F1 score if there's class imbalance in the data. Use these kind of metrics to get a sense of how well generalization is in the wild. But train test overfitting, for one, that could be a bad proxy because this deep double descent thing that shows that it starts to overfit and then suddenly it hits this interpolation threshold that isn't too well understood, but it's one of these things, deep double descent. So you can't really rely on this. In addition to this, it's the test split. What kind of distribution is the test split really? So there's another issue with this. It can fail in these added distribution tests like common sense reasoning tests, adversarial examples, or even just adding noise maps to ImageNet images in the ImageNet-C dataset. And then recently this WILDS dataset came out that I think is the best existing thing out there for testing additive distribution generalization. So Checklist is another paper. It won the ACLL 2020 Best Paper Award by constructing this set of tasks to evaluate linguistic capabilities, how well does it understand vocabulary, this set of tasks that are supposed to help get a sense of generalization with the model. So then another thing that I think is interesting is, does DALL-E generalize? So the generalization of generative models. There's this interesting paper on the steerability of generative adversarial networks that looks at what kind of images can you find in the latent space of a generator trained with the GAN framework. So it's kind of an interesting idea thinking about different ways of generalization and what kinds of deep neural networks generalize and how do we measure this. Here's a promising direction towards generalization metrics and kind of getting some sense of the performance of these models other than just doing a train test split evaluation. So what Checklist is a set of these different tests like testing negation, vocabulary, named entity recognition. It's this complete suite of different tasks that are used to take a pre-trained model, maybe it's trained with supervised learning, language modeling, anything like that, and then evaluate it in this evaluation framework. OpenAI recently released this DALL-E model that lets you put in a text prompt and then it'll generate an image. And this is amazing. This is a completely surprising and exciting advancement in deep learning. But particularly what makes it so exciting is that it seems to be able to disentangle concepts and recombine them in ways that weren't exactly configured in the training data set. So you imagine this training data set couldn't have possibly had an armchair in the shape of an avocado. But you're able to put in this text prompt and this generative model is able to generalize in the sense of disentangling these semantic concepts and then recombining them into a new idea and then producing an image that generates this idea. So this recombination is probably happening in the parameters of the deep neural network and these intermediate layers. And I mean, this is just an absolutely amazing achievement of deep learning. So this issue this discussion of do generative models generalize, I think is a really exciting topic with respect to generalization metrics, maybe generative data augmentation too. Imagine, say you have self-driving cars and you have these crazy edge case scenarios. Maybe you can just describe all these edge cases and you'll have some kind of text-to-video, text-to-image model that can render all these scenarios, and then you can almost brute force a data set to train autonomous vehicles and object detection, semantic segmentation, all this kind of stuff. So this is another paper on the steerability of GANs that I really like that explores to look for these data augmentations in the latent space of the vectors that produce these images to test this idea of generalization in generative models. The next key challenge with applying deep learning or limitation of deep learning is the challenge of learning from limited labeled data sets. Particularly in the pandemic response situation, it's tough to quickly get a large data set for a lot of these tasks like medical image analysis or misinformation detection. So the standard solution to this has been transfer learning. Transfer learning, again, just refers to pre-training on one task and then using those same weights for the next task. And this has been easier than ever to implement with TensorFlow and PyTorch frameworks. Things like doing import keras.models.applications, ResNet 18, as easy as these quick syntax, quick lines of code to load pre-trained weights of a lot of these popular computer vision models, and increasingly with things like Hugging Face's Transformers library to do the same kind of idea with transformers trained with natural language processing tasks like the mass language modeling, self-supervised pre-training. So self-supervised learning has been the hero of the story in overcoming the challenge of learning from limited labeled data sets, where instead of supervised learning with our small labeled data set, we do self-supervised learning with a larger data set, but from a somewhat in-domain composition of that unlabeled data. So some other interesting approaches include the MAML algorithm. MAML is a meta-learning approach for learning to learn fast. So the idea is that it's trained on a bunch of these meta tasks such that it learns a good initialization that can learn quickly. So maybe as that develops further, it'll become a more promising solution to overcome this problem. The other approach is neurosymbolic AI. Maybe new approaches to representation learning can also help with learning quickly and learning with less labeled data. The next limitation is data privacy. So particularly with things like ambient intelligence, I've had a time in my life where I spent a long time in the hospital, and I don't know if I'd be so happy if there was a centralized database that had every single thing I did while I was in the hospital from a camera up in the hospital room. So these are some of the different approaches that they discuss in this ambient intelligence paper on some of the things they do to try to have solutions to data privacy and simultaneously try something as ambitious as ambient intelligence and kind of this like deep learning surveillance in the hospital. One of the most exciting ways for overcoming the data privacy issue is federated learning. Federated learning is the idea of not having a centralized database, but rather you send the model weights to be updated on a local database, and then you just pass around the model weights. So you might have a centralized database of the model weights, but not the data itself. So this is one interesting idea of overcoming this problem of having some kind of centralized database and then still using data sets to train machine learning models. Some other interesting ideas include things like differentiable privacy, which has a lot more complexity to it, but next we'll link to something that is an interesting lecture on this. This is the lecture that I watched from Andrew Trask on Lex Fridman's YouTube channel, where I got most of my information about data privacy and privacy preserving techniques in deep learning like federated learning and differentiable privacy. So I highly recommend just checking out this lecture instead of me trying to explain it and probably messing up a lot of details. It's about an hour presentation, really great overview of data privacy and some techniques to overcome these issues. So when considering each of these applications of deep learning for COVID-19, like scientific literature mining, medical image analysis, or SIR spread modeling, it's important to think of these limitations of interpretability, generalization metrics, learning from limited label data, and data privacy. When we have applications like scientific literature mining for doing things like question answering, how can we be sure that it's going to generalize to new questions? When we're doing precision diagnostics, how do we know it's going to generalize to new patients? Maybe they have patient description variables that are out of distribution of our training set. And then also we need interpretability to communicate with doctors why our deep learning system is making the predictions that it's making. And then we also understand how many of these applications struggle to collect large labeled data sets, and in some cases this may be due to data privacy issues as well, and particularly things like ambient intelligence, having an eye for data privacy and being mindful of how to make sure there isn't people's private data being easily accessed by whoever might be trying to access it. So definitely I think it's interesting to think about these limitations and how they might hinder these applications and what we need to do in order to overcome them. Mentioned quickly in the survey is the connection with Francois Chalet's On the Measure of Intelligence. In my opinion, this paper has the best view of what it means to have an artificial intelligence system acquire a skill. Chalet defines skill acquisition as a function of prior knowledge, experience, and the difficulty of that is measured by the generalization difficulty, meaning how hard is it to go from this training set of experience into the wild and into these new test cases. So I think with respect to all these applications, from scientific literature mining to vision-based robotics and drug repurposing, how do we have our artificial intelligence acquire these skills through the use of data and deep learning algorithms? And I think this framework of thinking about it as prior knowledge, experience, and then measured by generalization difficulty is a really great way for thinking about and framing each of these tasks. From this presentation, I hope you're able to get a sense of an application of deep learning for COVID-19 that interests you and how to access an open data set to get started with it. Some of my favorite data sets that I surveyed are COVID-19, SciFact, COVID-X, and Mimic3. Personally, I'm now going to be devoting the rest of my PhD to working on scientific literature mining with COVID-19, SciFact. Also, as mentioned previously, I really believe in these machine learning paper data sets, like what's used in TLDR from the Allen Institute, as well as this archive data set. Because personally, I think the intuition of working with machine learning papers will work more for developing these systems than, say, working with these biomedical papers where I don't really know anything about it. And I'm not saying that it's like completely limiting, but it probably might make it a little more challenging than it needs to be for early prototyping of these deep learning systems. But aside from that, I think the COVID-X is a great data set for image classification, medical image classification. And then Mimic3 to me is this healthcare data set, ICU, patient stays. I think one of the most important ways of applying deep learning for changing the world. So then I think the first question is, how can I apply self-supervised learning to this? It seems like if you can have some kind of auxiliary task self-supervised representation learning, it's going to really improve the performance of the deep learning system. And in order to make that work, the question is, where can I find a massive unlabeled data set that's somewhat in domain? You don't want it to just be unlabeled data that's images as well as the downstream tasks as images. you want it to be like similar data. So if it's medical images, you want to use the Chexpert data set rather than say ImageNet. So then I think the next question is, has anyone applied transformers to the problem? Because it seems like transformers, if you can become an expert in, say, the efficient transformers like longformer, performer, reformer, these kinds of models, maybe transformer XL or the compressive transformer, these recurrent extensions to transformer, any of these extensions, I think, will have a huge impact because it seems like this transformer neural network is a winner and it's really, advancing deep learning. So then, if you have the resources, I think scale also seems to be something that tends to pay off. Some of the lessons that I learned from doing this literature review to gather applications for COVID-19 for deep learning. Before I did this, I had absolutely no understanding of, COVID-19, just trying to learn everything I can from the news and all these kinds of things. So in my opinion, the best way to learn about a new application for deep learning is to first understand the input-output format. Generally, how do we input data as these matrices? And then is the output, is it like a classification label task, or is it also, say, generating an image, or where you could output a matrix as well as these like logit vectors for classification, or it could be just a numeric output like a regression task. Understanding input output, I think, is important. Understanding what kind of data we have, is it unlabeled, and can we use self-supervised learning? I think these are some of the most important questions to ask when you're looking at a new application to apply deep learning to. But in my opinion, I still think prior knowledge reigns supreme in deep learning. So I think, surveying, natural language processing, computer vision, organizing the applications like that is because I think images and text are going to be, deep learning is going to continue to advance in those fields faster than, say, deep learning for biology or biochemistry. And it's not because they're not important, but I think it's because, we're able to use things like data augmentation that really inject prior knowledge about this data domain of images and text that I think really causes it to advance quickly. Thank you so much for watching this video explanation of our survey paper on deep learning applications for COVID-19. The original paper is linked in the description of this video, as well as many of these different surveyed works that have been presented throughout the video. Thanks for watching, and please subscribe to Henry AI Labs for more deep learning and AI videos.